Welcome to another edition of Admiral Science. I'm your host, Mr. Allen. This is Craddock Middle School's 8th grade science class, and this is another edition of Admiral Science. Today we're going to be reviewing atoms and elements. We've done a couple of segments on it, but today this is a comprehensive review of what you should know, getting ready for an assessment for atoms and elements in the 8th grade. Alright, so let's start off with the introduction of the atomos, or atom. The term Latin atomos was derived by Democritus, and today we call it the atom. So in 1803, this guy, Dalton came up with the theory of the atomic theory, and he basically gave atom the first physical structure we could imagine. And the difference between Democritus and Dalton is, Dalton, as we know with the nature of science, we needed evidence, and Dalton provided our first key pieces of evidence, and so he came up with this structure of the atom. Then in almost 100 years later, in 1897, Thomson was credited with coming up with our first subatomic particle. And Thomson said that we have electrons inside of this atom, and that it sits on top of this positively charged matter. And he gave the term electrons, and we started to take shape, and it's often called plum pudding. I call it a cookie, but people back then called it plum pudding. I guess that was popular. But plum pudding, and so it's like these balls of small circular balls were sitting on top of this large spherical structure. And so that is Thomson's model. Then as we transform into 1908, we come up with this model, and someone is credited with coming up with the nucleus. His name is Rutherford. Rutherford said that the nucleus was a dense, positively charged core surrounded by electrons. So as we see the agreement here that the electrons are there, but except for they circle around a nucleus in these orbit-style motions. Alright, so now we start off with this model of the atom with no structure, just a circular sphere, and then we come to this structure of atom with these electrons in it. Then we focus, now we have a nucleus, and Rutherford is credited with the nucleus. And then Niels Bohr said that this nucleus was positively charged, but it also had these neutral elements involved in it. Alright, so we call them neutral elements, the neutral particles. We call those neutrons. And we call those positive particles, we call those protons. And so now in our core, or our nucleus, is where our 99.8% of the mass of the element is at. So all of the mass, relatively speaking, all of the mass is focused inside this nucleus with the protons and the neutrons. Remember that, because that's going to play a role later. And then it said that these orbits around the nucleus contained electrons, and they were in fixed paths. So he created these energy levels, 2 for the first energy level, 8 for the next one, and so on and so forth. So these were the energy levels that he said electrons traveled on fixed orbits, and that the inside core was a positively charged protons and the no charge neutrons. And then that leads us to our present day model of the atom, and it said that it did agree with Bohr about the nucleus containing these protons and neutrons, and that it was all the mass. But it said that electrons didn't go in these fixed paths, but in a cloud around the nucleus. So now we have straying away from saying that orbits travel in fixed paths. So did Rutherford's model. If you can see, it has fixed paths, not circular paths all the way around, but fixed paths going in a dimensional style format. And then we have said, no, that's not quite right. It's in a cloud, and this cloud is primarily empty space with electrons in around it, around the nucleus. And this was comprised by Schrodinger and a few other scientists, Einstein being one that comes to mind, Weinberg, and the like. Alright, so the subatomic particle. So the atom is the smallest unit of matter, but the atom can be broken up. At first, during Dalton's time, it was thought that the atom could not be broken up any further, but now we know, based on, as we've seen our trajectory of how the atom transformed, we came up with electrons, then we found a nucleus, then we said the nucleus was made of protons and neutrons, and then we said that the nucleus is surrounded by a cloud where electrons orbit in. Alright, so now we know protons are the positively charged particles, the atom's atomic number. So the protons are the atom's atomic number. This number will never change. If you change the proton, you change the atom, you change the element. Alright, so the atom's atomic number is represented by protons. Alright, this number will never change. Neutrons are the atoms with no charge, and they can change, and when they change, it's called an isotope. Alright, so if you change the number of neutrons, notice how in one element you can have 24 as the atomic mass. For example, sodium can have an atomic mass of normally 22.99, round up to 23, but sometimes we've seen it with 24, sometimes we've seen it with 25, sometimes you can see it with 21. Alright, those different atomic masses, because of the neutron change, is called an isotope. Alright, when the neutrons change, it is called an isotope. The protons will never ever change. If you change the proton, you change the element. And then lastly, we have electrons, that are negatively charged particles, and they can change during chemical bonding. As we learn later on about chemical bonding, we understand that electrons can change, and especially, more specifically, the valence electrons will change. And we'll get into valence electrons later on. So protons, positive, neutrons, no charge, and electrons are negative. Alright, now the organization of the atom. So here we have the nucleus, and then we have the electrons in orbit. And this model is the Bohr model, and this model shows that the electrons in his model are in fixed orbits. We know that this is not true, but the reason why we use the Bohr model and why we use it is because it shows us what the electron cloud model can. It shows us the number of electrons, and specifically the number of valence electrons, because these valence electrons on the outermost part are called valence electrons. And so any electron on the last level is the valence electron. So for this element in particular, we have 1, we have 2, we have 3, we have 4, we have 5, we have 6, we have 7, and we have 8. And when an element has 8 valence electrons, it is said to be complete. That is the magic number that all elements want, is 8. Except for exception of hydrogen and helium, their complete number is 2. This is our periodic table, and you can see that we have some blues, some pinks, and some yellows. And these colors represent something on the periodic table that we're about to get into in just a second. So, but first, let's look at how our periodic table is organized. First, we know that our periodic table is organized by atomic number. All right, so we have the first atomic number down here and the last atomic number down here now. This is an older version of the atomic, but now we go all the way up to 118. And so 118 is our final atomic number so far. And so it is broken up into this structure. All right, and so it goes from 1 to 118, and each number represented is an atomic number. And then we said the atomic number is the same as the number of protons. Alright, the number of protons. And forgive me for the streaks, but sometimes the screen I write on does it. But the atomic number is the same as the number of protons. So essentially, when you change this number, see, we go from 1 proton to two protons, you have helium. Alright? If you go from 2 protons to 3 protons, you have lithium. If you go from 3 protons to 4 protons, you have beryllium. And it goes all into 118. So if you change the atomic number, which is the number of protons, you change the element. That's why this number never changes. So then it's also organized by periods. So all elements in period, this is period 1, this is period 2, period 3, period 4, 5, 6, and 7. Alright, remember that this is part of 6 and this is part of 7. And we write the numbers on the side. Alright, so the periods on, or the horizontal rows, which is the periods, the horizontal rows tell us how many orbits that the element has total. So all the elements in period 1 have one orbit, and we look at an orbit. So let's say that this is the nucleus. Those circles around the nucleus that we just saw, those are called orbits. And so all the elements in period 1 have one orbit. All the elements in period 2 have 2 orbits. All the elements in period 3 have 3 orbits. Alright, remember that this is our nucleus. So we have 1, 2, 3. So continue on all the way down to 7. You have up to 7 orbits. Alright, and everybody's last orbit should have 8. Alright, that's the magic number. Everybody's last orbit should have 8. And reactivity goes this way. So the elements on this side in group 1 are the most reactive. That means they can bind with just about anything. Alright, so they're the most reactive, and the elements over here are the least reactive, and they really don't bond with anything, because if we look at periods, which we're about to look at it in a second, I don't know why that did that, but if we look at periods, we're going to see that elements groups are important in determining a lot of things. And let me just erase this for a second. Alright. So these are the least reactive. That's because they're complete. Alright. So from left to right, we can predict exactly what is going to happen. So we can predict who these elements right here can combine with, and we can predict that these elements will not bond. Alright. So from here to here, we know from left to right, we can predict their properties, and it's doing it for some reason, but we can predict their properties, and I'm going to try not to write so that we can avoid the streaks, but we can predict their properties. Alright, and with groups tell us the reason why we know that this side is the most reactive, the least reactive, and this side is the most reactive, because our groups tell us how many valence electrons there are, and valence electrons are important because they are our key identifiers of chemical reactions. Alright, so the more you can react, the more reactive you are. The least you can react, the least reactive you are. So all the elements in group 1 have one valence electron. And remember that magic number of 8. So that means that they have a possibility of trying to find 7 valence electrons. Alright, the groups in all the elements in group 2 have 2 valence electrons. All the elements in group 3 have 3 valence electrons. All the elements in group 4 have 4 valence electrons. All the elements in group 5 have 5 valence electrons. All the elements in group 6 have 6 valence electrons. All the elements in group 7, and I do apologize, 16, this is their group number is called 13, 14, 15, 16, and 17. And all the elements in group 18 have 8 valence electrons. So what I was doing, and if you notice, I was calling out the second digit, because the second digit is the factor for all our double digits. The second digit determines the number of valence electrons. So 13, you look at the second digit, is 3. 14, you look at the second digit, it's 4. 15, you look at the second digit, it's 5, so on and so forth. So you look at the second digit to determine the valence electrons. And if we remember, valence electrons are the electrons on the last energy level. So when you do your models and you start doing it, and it tells you, so all the elements in group 13 will have 3 valence electrons. All the elements in group 14 would have 4 valence electrons. All the elements in group 15 would have 5. And that's 6. This will be 16. All the elements in group 16 have 6. All the elements in group 17 have 7. All the elements in group 18 have 8. Once you have 8 valence electrons on the last energy level, no matter how many levels, remember periods tell us the levels 1, 2, 3, 4, 5, 6, 7. No matter how many levels you have, if you have 8 on the last level of valence electrons, you're complete, and you're in this row right here. Alright, you're just like these elements right here. These elements are least reactive because they're already complete. They don't need to find another element to make them complete. They're already complete with their 8 or their 2 for helium, who has 2. Alright, so they're already complete. If we move right along, now when you look at an element, you look at a couple of key things. Here you have the atomic number, which is also the number of protons. Helium has an atomic number of 2, or it has 2 protons. Either or, it's the same thing. Alright, so this number right here tells us the number of protons. This number never changes. This is the element symbol. Alright, it's a shorthand way of us writing elements, and this is atomic mass. Atomic mass is you take your number of protons, you plus add it to your number of neutrons, you get this number. Alright, rounded roughly. Alright, so protons plus neutrons. Alright, remember protons, which is this number right here, this is your protons. You take this number, add it to the neutrons, you get this number. If you don't know neutrons, then you take this number and you subtract it from this number. And this will tell you the number of neutrons. Wow. Alright, if you know these two, then you know this number. So protons is protons plus neutrons equals mass. If you know the mass and the protons, you can easily find out the neutrons. Just like in math class, if you isolate the variable you're trying to find, neutrons being n, you take m minus protons and you'll get your neutrons. Alright, so either way, if you know 2 of the information, you know the third. Alright, so let's look at it. So atomic element for each one, we're going to find out the atomic number, the neutrons, the electrons, and the atomic mass. Alright, so for example, helium, which we just saw, has an atomic number of 2. That means it has 2 protons. Alright, and in a stable element, the number of protons will equal the number of neutrons. Electrons, I'm sorry. They will equal each other. So if it's 2 here, then it's 2 here. Alright, so if we look on our periodic table, it says 4.003. We're going to round out to 4. Alright, and you take 4 minus 2 to get this number, which is 2. Alright. Alright, let's look at calcium. Calcium has an atomic number of 20. So we write 20 here. It has an atomic mass of 40.08. So 40.08 rounds out to 40. Alright. And we said that the protons equals electrons. So that 2 is 20. Alright. So then we take 40 minus 20, and that gives our neutrons, which is 20 as well. See how that works out? Alright, so let's look at nitrogen. Nitrogen has an atomic number of 7. Alright, we said protons equals electrons, also 7. Alright, so then atomic mass is 14.007, so we run out to 14, and again, this will be perfect. As neutrons is 14 minus 7 is 7. Alright, for oxygen, alright, we have an atomic number of 8. We have electrons 8, and then we're going to create an isotope. I'm going to say that the atomic mass, let's say if the atomic mass of oxygen is 17. Alright, so remember, you can change the number of neutrons, you create an isotope. Alright, so we changed the number of neutrons and gave it an atomic mass of 17. How many neutrons do we have? 17 minus 8 is 9. So we have 9 neutrons. Alright, so remember, atomic mass subtracted from the atomic number will get you the number of neutrons. Alright, so let's go through some more of our periodic table. And another category of groupings that we do with our periodic table is metals, nonmetals, and metalloids. Alright, as you can see, all the greens are metals. Alright, all the purples are metalloids, and all the nonmetals are orange here. Alright, so our metals are broken up into categories here, and typically on a periodic table you'll see a zigzag line, and the elements that are on the zigzag line, as you can see, are our metalloids, and they're the purple. All the elements to the left of the zigzag line, they're the metals. All the elements to the right of the zigzag line, they're the nonmetals, and all the elements on the zigzag line, they're the metalloids. Alright, so some properties of metals, nonmetals, and metalloids. Our metals are shiny and malleable. Malleable meaning they can be molded without breaking. our metals are also ductile, which means they can be formed into wire, like copper. They can be formed into wire, and they're good conductors of electricity and heat. Our nonmetals are dull and brittle means easily broken. And they're poor conductors of electricity and heat. Alright, they're poor conductors of electricity and heat. Alright, and our metalloids are those that contain both properties of metals and they contain properties of nonmetals. They are sometimes used as semiconductors in chips because they need properties of both. And metalloids are like our hybrid. They take some of our best qualities of metals and they take some of our best qualities of nonmetals. Alright, and they have the properties that are essential in certain electronics, especially those that have to heat up and continuously stay on, like computers. Alright, and we get into understanding metals and nonmetals when we talk about chemical bonds and electrons. And an interaction between elements is known as a chemical bond. When elements come in contact with each other, they form chemical bonds. And as we said before, valence electrons are key in this. So again, as a review, all the elements, these are our groups. So we have group 1, 2, 13, 14, 15, 16, 17, 18. Alright, all the elements in group 1 have one valence electron. Notice here, one valence electron. All the elements in group 2 have two valence electrons. 1, 2. All the elements in group 13 have 3. Look at the second digit. Alright. All the elements in group 14 have 4. All the elements in group 15 have 5. All the elements in group 16 have 6. All the elements in group 17 have 7. And all the elements that are in group 18 are complete, as they have 8. With an exception to helium, its complete number, as we said before, is 2. Alright, so here's our valence electrons, 1 through 8, based off their group number. And if we remember, we look at the second digit, 3, 4, 5, 6, 7, 8. Alright, and we can see here 1, 2, 3, 4, 5, 6, 7, 8. Alright, so how many valence electrons does this element have? So let's look at it. Remember, these electrons, they won't change in the chemical bond because they're already complete and they are already finished with their orbit. So valence electrons are determined by the electrons on the last level. So are chemical bonds. They're determined by the electrons on the last level. So we have 1, 2, 3, 4, 5, 6, 7, 8. Alright, ions and ionic bonds. Ions are elements that have lost or gained electrons. Alright, so if an element has lost or gained an electron, it's known as an ion. Ionic bonds are formed when a metal transfers its valence electrons to a nonmetal. So for example, lithium, it has one valence electron. It's in group 1. So it has one valence electron. Alright. To make lithium complete, it can either grab 7 valence electrons or simply give away 1 and complete itself with 2 valence electrons for the first level. So let's look. It's going to, and fluorine here has a total of 1, 2, 3, 4, 5, 6, 7 valence electrons. It can either give away 7 valence electrons and complete itself with 2, or just add 1 more. And that we all would agree that adding 1 more versus getting rid of 7 is a lot more easier. So once lithium gives away its 1, this energy level then goes away. And as we know, the maximum number of electrons on one level is 2. Alright, so 1, 2. Alright, so it completes itself because then it has a complete set of valence electron at 2 for one orbit. Alright, and fluorine completes itself because on the second orbit it can hold up maximum 8, and it will now have its 8. 1, 2, 3, 4, 5, 6, 7, and the one from lithium makes it 8. So when an ionic bonds are formed with metal, when a metal transfers its valence electron to a nonmetal. So lithium being a metal and fluorine being a nonmetal made this bond work perfectly. Alright? So metal, non-metal. The metal gives its valence electrons to the non-metal. Alright? And covalent bonds are formed when elements share their valence electrons. So covalent bonds form when nonmetals and another nonmetal share electrons. So for example, we have two nonmetals. We have a hydrogen and oxygen. Oxygen was in group 16, has 6 valence electrons. 1, 2, 3, 4, 5, 6. Hydrogen being in group 1 has 1 valence electron. So they're going to share, because if hydrogen shares its 1 valence electron with oxygen, who also shares back, it now has 2 valence electrons. And because there are 2 hydrogen with 1 valence electron each, if oxygen shares its electron and they share back, oxygen now has a total of 8. So remember we said if you have 1 orbit, you complete yourself with 2. If you have more than 1 orbit, you complete yourself with 8. And oxygen now has 8 valence electrons. So, and covalent happens when a nonmetal and a nonmetal share electrons. Alright, so let's look at, name that bond. So let's look at sodium. Sodium is a, if you look on the periodic table, it is to the left of the zigzag line, so it is a metal. Chlorine is a nonmetal. And NaCl is another way of saying salt. This is salt. And it is an ionic bond. Alright, carbon and hydrogen. Carbon, being on the right of the zigzag line, is a non-metal. I don't know why these streaks keep happening. And hydrogen is a non-metal. So a non-metal and a non-metal make a covalent bond. Alright, calcium. Calcium is a metal. And selenium, that's what it was. Selenium. Selenium is a non-metal. And that, a metal and a non-metal, is an ionic bond. Alright, lastly, lithium is a metal. And fluorine is a non-metal. And it makes a ionic bond. Alright, so remember, metal, non-metal is ionic, non-metal and non-metal is covalent. Same with water. This is water. Water is one of our best known covalent. Non-metal and a non-metal makes it covalent. Alright, so that was the end of our review. Review. In preparation for the upcoming assessment, my suggestion is that you go and review any concepts within the video you are still unsure. Go back, rewind. If you don't know something, if you did not get it the first time, go back, rewind, replay, and understand it more. Alright, practice. Try to quiz yourself. Make sure you don't go to the slide. Once I pull up the tables, pause it. Try to do the tables yourself, redo it, see, oh, this how I understand, especially with the metals, non-metals, what type of bond, things of that nature. If you have to quiz yourself, what are the atomic structures, what are the subatomic structures of an atom? All right, what are their charges? How big are they? What's their relative mass? All of these things can be reviewed. All right, preparation is key. Education is the passport to success. For the future belongs to those who prepare for it today. All right, so if you prepare today, you'll be ready for your future tomorrow. Alright, again, if you have any questions, please leave it in the comment section of today's video. I am more than happy to help you, and if you need to, review. This has been another edition of Admiral Science. I'm your host, Mr. Allen. I look forward to you in our future segments. Thank you.